And let's get ready for the first presentation of the day, actually, to kick off the conference properly. And that will be held by Andrey Meshkov, who is the CTO, founder, and owner of AdGuard. And you've all known him for his expertise in app blocking and also on online privacy. And his presentation is called System-Wide App Blocking on Apple Devices. And as you probably know, Apple has introduced a new system-wide URL filtering framework that can filter full URLs while preserving user privacy. And AdGuard has actually been one of the first ones to adopt it. And Andrey, will basically talk about how the framework works, how app blockers can leverage it, and he will share insights from their implementation work of it. So, Andrey, where do I have you? There you are. Please give a big round of applause for the first speaker of the day. Hello.
Thank you.
Actually, also it might be more convenient for the one or the other person. There are stairs here, or you take a big step from wherever. Up to you.
Hi, everyone. Just a moment. I'm getting used to all the high tech here. Yep. Do you work? It works. Great. Hi, everyone. To those who don't know me, my name is Andrey, and I'm the CTO and co-founder of AdGuard. And I'm super happy to welcome you to our home turf here in Limassol. Today, I will be talking about Apple's new API that enables system-wide filtering. I chose this topic because this API is quite different from what we're used to working with. It introduces several interesting innovations in how system-wide filtering can be implemented. Usually at these summits, we talk a lot about browsers and web extensions, and this is perfectly fine. But we shouldn't forget that content filtering is a broader topic. And I believe that looking at the challenges we face when implementing system-wide filtering can offer also valuable insights into how browser-based filtering may be improved in the future. So what exactly do we mean by system-wide filtering? System-wide filtering is essentially the ability to intercept and block web traffic from any applications, not just browsers. Achieving this inside browser has always been relatively easy, thanks to the extensions. And even with Manifest v3, the browser still provides clear, well-defined API for content filtering. Operating systems, on the other hand, are a completely different story. None of them offer dedicated API for this, so we have to rely on different platform-specific techniques, and each comes with its own drawbacks. You might ask, why does system-wide filtering even matter? Well, there's a very good reason for that. According to recent studies, browser-originated traffic makes up less than 15% on mobile. On desktop, browsers still dominate with 55 to 60%, but overall, across all platforms, only about 30% of total internet traffic comes from browsers. The other 70% from apps. And that's where the real privacy challenge lies. Tracking inside apps is often far, far more invasive than on websites. Apps can access more personal data, interact directly with device resources, and use persistent identifiers the websites just cannot use. System-wide filtering, historically, has always been one of AdGuard's core focuses. The very first version of AdGuard was a Windows application that blocked ads at the network level, and over time we expanded it to every major platform and went even further with AdGuard DNS and AdGuard Home. That's why this topic is especially interesting to me personally. There's still a lot of room for improvement, and I'm very glad to see that one of the operating system vendors is finally paying attention to it. To understand my perspective, you first need to know how system-wide filtering began, how it works today, and what challenges we're still facing. And many of you probably know this, but for some it might be a surprise. Ad blocking actually began with host files. And you can see, by the way, as on this slide, a snippet from Peter Lower's block list, like 27-year-old block list. Where's the guy? A round of applause for Peter. But host files are pretty well limited. There are tons of limitations. I will not list them, but still, this was where it all started. Then came DNS sinkholing, basically the same idea as host files that solved like a couple of problems of it, but is still limited. Can only block domains and can be bypassed if needed. So DNS sinkholing helps, but it is not a complete solution. Next come proxies. This approach was extremely popular in the early days of ad blocking. Many of the classic tools used it. You might remember AdMuncha, for instance, or even early versions of AdGuard. The screenshot you see here is from 15 years ago, when AdGuard essentially worked as a local HTTP proxy. The main advantage of a proxy is that it can filter based on full URLs, not just domain names, and as long as the traffic is not encrypted. And even if it is, the proxy still can see the domain names. But the first technical challenge for system-wide filtering is intercepting traffic and routing it to your filter, DNS or proxy. And different platforms require different techniques. You can see this long list on the slide. All of these methods are non-trivial to implement. They are easy to get wrong, and they frequently run into compatibility issues. Yet, they are the primitives we must live with if we want to filter traffic system-wide. But even if we solve all the previous challenges, there's still one big problem left. We need full URL visibility for accurate filtering, and the current internet is completely encrypted. So what do? We do TLS interception. Why is that important? Let me give you two examples. The first one is Facebook's ad network. Facebook serves both legitimate content and tracking requests from the same domain, graph.facebook.com. And without access to full URL, blocking the whole domain will simply break Facebook itself. The second example is pretty new. The Internet Advertising Bureau came with a new proposal called Trusted Server quite recently. I won't go into the details with it here, but in short, it moves ad auctions to the server side and delivers ads from the publisher's own domain. So basically making them appear as first party. Right now, the only reliable way to inspect full URLs is to run a proxy with TLS interception, but that, however, is an extremely complex task. You basically need to do the same what the browser does with all the TLS validation. So someone has to observe your traffic for filtering to work, whether it's a browser extension, a VPN, or an antivirus. It's just unavoidable. Ideally, when this happens locally on the user's device, that's safer because the data never leaves your device. But even that requires trust, and history shows that this trust can be betrayed. So while local filtering is preferable, it is not a guarantee of privacy. Users still must place their trust in whoever runs the filter. So what should an ideal system-wide filtering solution look like? First of all, it has to support full URL filtering. That's essential. Next, it should offer broad filtering capabilities. Just blocking requests is not enough. Sometimes you need to modify or redirect them or inspect responses. Third, it should also be able to handle very, very large block lists. Fourth, and yet updates must still be fast and efficient. And of course, it must be private by design, meaning we shouldn't need to know which websites a user visits. We just apply the rules locally. And still, the system should give us some kind of feedback, at least for basic starts. And finally, the last one, but also very important, we need proper debugging tools for both developers like us and for filters maintainers to troubleshoot their rules effectively. Finally, to Apple. About 10 years ago, Apple became the first browser developer to introduce a dedicated content blocking API. Now, a decade later, they have taken another big step, this time at the operating system level. For the first time, Apple is providing an official API for system-wide filtering. On paper, this is great news. And frankly, it is something that we have been waiting for. It is an exciting opportunity for anyone working in privacy and network filtering. So let's take a look at how this API actually works. And we will start with a very, very high-level overview. So first, your app registers a special URL filter extension within the operating system. Then to activate it, the system performs an authorization step. It communicates with your server to verify the configuration and credentials. And once that's complete, the filter enters the running state, and from that point, the system starts using it to check request URLs. When the URL filter is active, it examines every web request made by any app on the system. For example, when an app wants to send a request to example.org/tests, the system first splits the URL into small sub-URLs. These are checked against a local pre-filter to quickly decide which URLs can be classified as safe. The remaining are sent to your remote server for further verification. And based on the server's response, the system either blocks or allows the request. Now, it's easy to see how a naive implementation of this would be a privacy nightmare. To address this, Apple introduced several clever design decisions that aim to preserve user privacy while still enabling effective filtering. The entire URL filter API is built on top of several modern privacy technologies. First, there's privacy paths, which is used for user authentication. Next, there's a private information retrieval, or PIR service, used for server lookups, which is accompanied by a Bloom filter, which acts as a local pre-filter. And finally, there's oblivious HTTP. All of these tech are quite new and cutting edge, so it's fascinating to see Apple using them in a real-world system like this. Let's take a closer look at each of these components. And the first component is Privacy Pass. It is a modern privacy-preserving authentication system. It lets clients obtain anonymous tokens that prove legitimacy without revealing the identity of the client. As shown on the diagram, when a client sends a request to the origin server, it can ask, the origin server can ask for a valid token. The client then has to contact the second entity, the attester, to confirm its eligibility. The attester approves it, and then the third entity, the issuer, generates a token for the user, for the client. The client then grabs the token, sends it to the origin, and origin verifies it without contacting the issuer in the real time, just using the public keys published by the issuer. The core idea here is separation of roles. If the origin and the issuer remain independent, authentication stays anonymous. The server knows the token, and it can check that it is valid, but not who the user is. So that's how it works in theory, but let's look at how Apple actually uses it in the system. And the thing is that in Apple's case, the client first authenticates with some persistent identifier. With some persistent identifier, like a user account, to get short-lived privacy tokens. And then for every server lookup, PIR lookup, it redeems one of these tokens. Looks very similar to the original idea, but here's the key point. Unlike the ideal design, both the issuer and the origin in Apple's system belong to the same entity, to the developer. And since the developer controls both, tokens can potentially be linked to the users. So, true anonymity depends entirely on the developer's implementation and developer's will. Now let's talk about the second component, private information retrieval, or PIR. In simple terms, PIR is a family of cryptographic protocols that allows a client to retrieve data from a server without the server knowing what actual data was requested. the idea is not new. It's been explored since 90s. And the oldest example of a PIR-like system in wide use is Google Safe Browsing. It follows a similar principle, although without the heavy cryptography. Apple's implementation of PIR is a much more sophisticated system. It relies on cryptography a lot. I will probably save us some time and not go into a lot of details here, but it follows the same principle. The client asks for an item, but the server does not know which exact item was requested, and returns a bunch of items that might kind of work. And the client then does the second check, locally checks, so is the item that is requested is there in the response. And if it is, it considers that, well, the item was found. Basically, this is what happens with URL checking. And, well, thanks to a lot of encryption, so you just count the number of words encrypted on the slide. It looks like a private information retrieval, right? But let's talk about performance now. Apple's PIR system is quite heavy on resources. Each query can be around 30 kilobytes, which is quite large for an API request. And a single lookup may take over 100 milliseconds, even under ideal conditions. And as you would expect, the larger the database, the slower each lookup operation becomes. To solve this problem, Apple's PIR allows sharding, splitting the main database into smaller parts. The server defines several shards, and when checking a URL, the client computes its shard number using a special function, the sharding function. And it includes the shard number in the request. So this speeds up queries, but introduces another potential privacy leak. With many, many shards, a shard might correspond to a single URL, basically revealing what the user is checking. Can this risk be mitigated? Yes, probably. Apple could mitigate this by enforcing a minimum shard size or a maximum shard count, but that's not here yet. I hope they will consider doing that in the future. But even sharding is not enough if the client has to send every single URL to the server. So Apple added another optimization step, a pre-filter, which is basically a Bloom filter. I won't go deep into how Bloom filter works. Briefly, it is a very space-efficient and fast structure that answers a question, is this URL in the data set? And the possible answers is definitely not, or possibly yes. And if possibly yes, we need to do the remote check. The result is that most lookups never leave the device. And finally, the last component is oblivious HTTP. Privacy path ensures anonymous authentication. PIR hides the query. And oblivious HTTP removes the final identifier, the user IP address. It separates the client from the server using four parties. The client, the user device, the relay, which belongs to Apple, the gateway, which belongs to the developer, and the target server, PIR or privacy path. The client encrypts the request for the gateway so that only the gateway could decrypt it. And the relay that belongs to Apple just forwards it. So what we achieve? The relay does not know what's inside, so Apple doesn't know what's inside of the request, and the gateway doesn't see the user. So we kind of were able to hide their IP address. The idea is simple, well, and it works. But even if you managed to get everything working, there's one last step, Apple's review process. Before your app can use the new API, both your PIR service and your oblivious HTTP gateway need to be reviewed and approved by Apple. And be prepared, it can take like months. Plan ahead if you plan to build around this API. So how good is Apple's URL filter? In the first part of the talk, there was a list of properties of an ideal system-wide filtering solution. Now let's revisit that list and see how Apple's new URL filtering API measures up against those expectations. And the first point is full URL filtering. Checked. No questions here. Now let's move to the second point, broad filtering capabilities. Unfortunately, absolutely not checked. Apple's system lets you block requests, and that's about it. There are also several important limitations on top of that. You cannot unblock individual domains yourself. It's all or nothing. Either the entire block list is enabled or disabled. And you cannot switch between different block lists. Each app can only provide a single list. Now, there are some theoretical workarounds, but those approaches are more like hacks than proper solutions. The API is not designed with this in mind. Then support for huge block lists, and this one also gets a check mark. The API was well prepared for that, even though introduced a privacy issue. The next point is about how quickly block list updates can be delivered to the users. And here, again, Apple also gets a check mark. The API supports automatic updates, and the minimum update interval is 45 minutes, which is actually quite good. And what I would like to add is that it's very not typical to Apple. Usually, keeping something up to date, if you're just an app, is very problematic on this platform. Now, the next point is a bit more complicated. For me, private by design means that when an app uses this API, the user should remain completely anonymous. And there's no possible way for the developer to learn who they are or what they do. And while that was clearly Apple's goal, the whole architecture is built around different privacy technologies. In practice, there are two big loopholes that a developer could exploit to re-identify the users or track their activity. They can be addressed, though, and I really hope that it will be done in the future revisions, but not right now. So, does the API provide any feedback to the developer about how it's actually working? None at all. The app has no way to know whether its URL filter has blocked something or even checked something. In other words, a complete black box. Stop. And finally, debugging tools. No built-in tools, nothing. And as you can imagine, troubleshooting a URL filter is a very, very, very difficult task. And finally, despite all the shortcomings we've discussed, I want to end on a positive note. This API is infinitely better than not having one at all. It is a big step forward, the first real attempt by any operating system vendor to make system-wide filtering both secure and privacy-preserving. So I'm genuinely grateful to Apple for taking this initiative and being the first to think seriously about this use case. It is not perfect yet, but it is a very promising start, and I'm excited to see how it evolves in the future. And if you decide to experiment with Apple's PIR system, I prepared a list of tools that can be useful to you. First, Apple provides an example implementation of PIR and Privacy Pass services. It is not production ready, but it's a great reference to understand how all the components are supposed to work together. To make testing easier, I have built a small command line tool that can simulate the PIR and Privacy Pass flow. It's open source, available on GitHub. Next, the Bloom filter. Apple didn't release any official code for building one, and their documentation on it was initially quite vague. So I created a Swift library that can generate Bloom filters compatible with Apple's URL filtering API. For Oblivious HTTP, Cloudflare provides both a reference library and a ready-to-use server implementation. And finally, if you need to test your Oblivious HTTP setup, you can use my long-term side project called GoCurl. It is basically a Go-based re-implementation of curl with extra features like built-in support for Oblivious HTTP. That's it. Thank you, everyone, for your attention. I'm ready to question.
Thank you for that. That was really interesting. It's amazing that they provided this API.
Do you know if they're still developing it? Is it still inactive?
Yeah, it is very new. So basically, this PIR API initially was developed for the previous iOS version, and the idea was it was used for the leave caller ID issue. If you use an iPhone, you can now in an app enable some app that shows you who calls you and blocks people, like it blocks spam. And this new API, enables this to work in a kind of a private way, but it appears to not that private. So be kind of wary about which app you use. And they extended this API for URLs in this new version in iOS 26 and macOS 26. So there's a big chance that they will extend it further. Hopefully, if they have enough feedback,
The other question I had was, so you think that one of the requirements or asks is that it has feedback on the blocking apps, but isn't that sort of against the private by design?
Depends on what kind of feedback we're talking about. So there are several approaches that can be taken. First, you may report feedback in different time, not at the time when it occurred, but like very at a different moment. Then, we would be happy if they at least report a sheer minimum, at least report that you work, report that you check something. I don't even ask for a domain name, just report something. Not there yet. And we need help.
Thank you. Really interesting talk. So I'm curious if you have tried to submit that proof of concept you have of the privacy issue to Apple.
We did submit it to the review, but from what I learned is that from forums, okay, so it may take months for them to respond. So, but we did build it, and we submitted it already. Waiting for them now.
Okay, cool. And I'm also curious if you know what is the justification for having this whole complicated encryption system between.
Because if you have all existing privacy buzzwords in your system, then your system is super private. Isn't it obvious?
Why not just encrypt everything locally and have it run locally?
That's a good question, by the way. So the point is that initially it was developed for this leaf caller ID, right? So in databases of block lists of spammers are huge, very big. These are so big that you do not want to bring them locally. You cannot bring them locally. So you need the same actually applies to Google Safe browsing. The block list of phishing URLs is just too huge. So you need this.
I see. So it really does have support for huge.
Yeah.
Okay, yeah. Cool. Thank you.
No. Asbol?
Yeah.
So if you may speculate, if you would be the one to bring it to Android, would this have to be implemented on the Linux level?
On what level?
On the kernel level, on the Linux level.
Apple, for instance, doesn't do that on the kernel level. So what they do, and actually I haven't talked about this, but their API can be bypassed if you use just sockets directly. So and they do that with many network level stuff. They only enable it for URL session or for WebKit. And everything else kind of goes around it. So
full system-wide filter.
Yeah, and for instance, on macOS, if you install a URL filter, it will not cover Chrome because it uses sockets directly. But for that, they provide so-called participation API. So you can, if you're a Chrome developer, you can call a special method that is this URL blocked or not? Apple tell me, and it tells, and then you kind of can participate and kind of block the request. and I opened an issue in Mozilla's Bugzilla about that, and someone opened in Chrome, so maybe they will participate. That would be great. But, well,
Thank you. Yeah, one more question. Did you get to observe if this applies to requests made by a system itself?
it seems so, but not to all, because again, Apple doesn't use URL session for every APIs that they have. So for those where they use sockets directly, well, it doesn't.
So in theory, you could use this to log some telemetry from Apple, maybe?
If only I had like debugging tools. Figuring out what is inspected, even when you have like debugging log profile installed, is impossible. So because Apple somehow thinks that this data is private, and because of that, it doesn't write it to the log. So it checks something, but what? Who knows?
Okay, thank you.
A question? No? Okay, then seems we're good. Thank you, Andrey. Thank you so much.